In this video, we're going to look at fitting data to curves. We're mainly going to look at the theory behind fitting data to curves. And we're going to start with lines, but then go into general curves, trying to fit data to any kind of curve that we might have. But we'll start with fitting straight lines. So, for example, let's say if you wanted to have a best fit straight line to this data here, there'd be a lot of possibilities. You could make a line maybe down here or here or here or here or here. And the main idea, though, something that would make sense then, is to fit a curve or a line or curve such that the total error will be a minimum. In other words, we would like to fit a line such that if we took, say, the difference between our line and every point of our data, that we would have the smallest total error. Obviously, if we made a line that went, say, just over here, some of these points would be right on the line, but these points would be far away. If, on the other hand, if we picked a line over here, we could get right through many of the points, but these would have big errors. So probably the best line is probably going to be somewhere in the middle, where when we add up all the errors, they're going to add up to be a minimum. That's kind of the goal, whether we're fitting lines or curves, to fit the line or the curve such that the error, the total error, will be a minimum. And we're going to take a look at that. Like I said, first we're going to look at lines. So let's say, suppose we have a bunch of data points. Suppose we have data points. And let's say we have one point x naught, y naught, another point x1, y1, another point x2, y2. And let's say that we go all the way up to xm, ym. So we have all these points, for example. Now notice, since we started at x naught, we have m plus 1 data points. And again, it's 1 through m plus this one here. So we want to fit the best curve to these points. And suppose, again, let's take the case of a straight line. Suppose we wish to fit a straight line. We wish to fit a straight line to these points. Again, that would be like, let's say y equals ax plus b. And let me write it this way. Ax plus b equals y. And so we want to use something of this form. And now we could rewrite this, and we could make this ax plus b minus y is 0. So, normally if we have a straight line, we'll have certain values of a and b, and all the points on the line will satisfy this equation, which means it also satisfies this equation, so that when you put your points on the line for whatever a and b that you have, the left side will end up being 0. That would be, so if all your points are right on the line, the left-hand side is going to be 0. Now, let's say we're going to fit to a line, but not all the points are going to be on the line. So let's consider our data points. Let's say consider say a typical data point. Let's say, xk, yk. And again, suppose we have this line, and let's plug our point into this equation for the line. And xk plus b minus yk. And now, as I mentioned, if the point is on the line, this is going to be 0. So when we put our point in here, this will be equal to 0 if our point is on the line. And it's not 0 if our point is not on the line. Like this. And so this would be like, say, the error that we would have if we have a given line and we put our point into here. Whatever we get is going to be our error. So this is going to represent our error for each point. In other words, for each point that we put in. So our error is k plus b minus yk. And if we put the absolute, well, I want to put the absolute value around the error. So this represents the error right here for a given point. And the reason I wanted to put absolute values here is because when we add everything up, all of our errors for all of our points, we don't want them canceling out. Because if we don't put the absolute values here, if something is, say, 0.5 above and another point is 0.5 below, in other words, if we get a positive 0.5 in some cases, a negative 0.5 in others, they'll cancel out. So it would look like things are really good. So we want to find the absolute value of the error. And now the strategy is we want to choose our A and B that represent our line. Of course, this is going to be like the slope and the y-intercept. We want to choose those. So our strategy is to choose A and B such that the sum of all of those errors the minimum. In other words, we want to choose A and B such that when we add all these up, that's going to be a minimum. So, and that's another way to say that, that is we want this sum we want the sum of all these errors to be a minimum. Now, one of the things in when we're dealing with absolute values and we start taking the derivatives and so forth, they can be hard to work with. So in this context, the absolute values are difficult to work with. So instead of trying to minimize this, we will minimize the square of that. A lot of times when you're trying to minimize or maximize the square root or something, it's much easier to maximize or minimize the square of that something. And again, it'll give you the same results. So again, this is easier to work with. And we're going to give this a name. Let me call this psi. And you can really give this any name that you choose. I think the textbook that I originally used when I was doing this used psi, so we'll use this. And notice we're going to consider this a function of A and B, because you see what's happening here is we're summing up all these points, and these points are the xk's and the yk's, and the variables are going to be A and B here. Note the variables for our, when we deal with a function, will be the A and the B. So we'll consider this thing a function of A and B. So we want to minimize this function here with respect to A and B. And so you remember, anytime you want to minimize something, you have to take the derivative of this. So we're going to take the derivative of this with respect to A and B. So let me go delta psi. Again, if you don't want to use this Greek letter, you can just give it a different name. So I'm going to take the derivative of this thing with respect to A. And that would mean, of course, when we take the derivative, bring the 2 forward. And you could actually bring it out front if you wanted to. Let's bring the 2 out front. Remember, constants you can always bring out in front of the summation. And again, we're going to have AX plus B minus Y. Again, we're using the chain rule. bring the 2 down and make this a 1. Then take the derivative to the inside with respect to a. So taking derivative to this with respect to a is just going to give us xk. And do the same thing with b. Take the derivative of the function with respect to b. And again, we're going to take the derivative now, the inside against the chain. We'll take the derivative of the inside with respect to b. And we just have a b here, so the derivative of that's just going to be 1. And again, whenever we want to minimize, we take the derivatives and set these equal to 0. This. But now let's see, how are we going to work with this? This is going to be difficult to work with the way it is. However, we can first of all, of course, multiply this xk in here. But remember, we can kind of break up these summations. And same thing here, we can kind of break up these summations. So I'm going to, again, make this whole system, each of these equal to 0. Now that taking derivatives, I can kind of ignore this notation over here and just put these together. And like I said, I'm going to make these into all separate sums. And let me go ahead and do that. Now, before we do that, notice that we have a 2 on the left-hand side. Again, these are kind of our equations. We have a 2 on the left-hand side, and it's multiplied times everything here. So we can divide both sides by 2. Remember, you can always divide both sides of an equation by a non-zero constant. So the 2 will go away. And then this 2 could also cancel, so we can get rid of the 2's. And then, as I mentioned, we'll multiply this x in here, distribute it. Of course, this is just 1. Then we're going to separate each of these summations. So when I did that, I got this right here. Again, I multiplied the xk, got xk squared, bxk, yk, xk. And then down here, this is just a xk, b minus yk, etc. And so we're making a lot of progress here. And again, we're working with this system of equations. Let me just put sort of a line here, kind of keep them together. And now the last thing we want to do, remember, if something is not, does not have an index in it, we can factor that out. So we can factor out the A here, the B here. Now we can't factor anything out here because they're both involved with the index. However, we can bring this over the right-hand side. So let's do all those things. So we're going to have A summation xk squared plus b summation xk, and bring these over to the right-hand side, yk xk, and down here, xk. And I'm going to bring the b out, and that's just going to leave us with 1. And like I said, bring this over to the other side here. And again, these are all from k equals 0 up to m. Like this. And notice this over here, this is just summing 1 up from k equals 0 to m. So we're summing it up basically m times and then plus 1 because we're starting at 0. So this right here is going to be b times m plus 1, like this. And just to simplify things, let's assign some names to each of these. So let's assign, again, this is kind of the standard way to do this, assign P to this summation here. I'll assign Q to this one. I'll assign, let's say, R to this one. And finally, I'll assign S to this one here. Again, I'm using kind of standard notation that they often use in textbooks. And let's see if I got everything. We had a couple of these. We had an XK here and XK here. And then we had this over here. And now let's replace these with what we have here. This is going to be S up here. And that's going to be A times S. And then over here, we're going to have B times this one, that's P. On the right-hand side, we have R. And then down here, that was P, a P. And then here we have B times M plus 1. And on the right-hand side here, we have what we're calling Q. So there's our system. It looks like much reduced here because don't forget, we know all these points. These are simply those points or data points. This is just going to be the X value and Y value of every data point. So we can solve this. And so let's turn this into a matrix. We can factor out the A and the B because remember, that's what we're solving for. We're trying to minimize this function based on A and B. So let's factor that out. So we'll factor out the A and the B on the left-hand side. So we'll have AB, and that's going to leave us with S, P, P, M plus 1, like this. So I factored out the A and the B. And then on the right-hand side, we just have our RQ, like this. Now you can go ahead and solve this. And so by solving this, you'll get the solution. You'll get your best fit straight line. And again, remember, so what we've basically done is come up with a system in which this is P, Q, R, and S. We can calculate these values and put them in here and then solve our system. And let's do a quick, real short equation here. Let me do an example, Let's find the best fit And let's say we have this data, X, Y. Let's see, our X values are 1, 2, 3, 4. Our Y values are 0, 1, 1, 2. So let's go ahead and do this. So, solution. I'm saving space. So I'm going to start the solution over here. We want to fit the line to this. Now notice we have, according to the notation we had before, we were going from like 0 to M. So here we have, this is going to be, say, our 0 point. So we have M is going to be 3. And we have 4 data points. Because remember, our total data points are M plus 1. And now let's go ahead and use what we have over here. Sum up your P values. Excuse me, sum up your X values to give you P. So P, which is the sum of our XKs. I won't put the index here, but because you know what I mean. So we're just summing these up. 1 plus 2 plus 3 plus 4. What is that? 5, 9. That's going to be 10. And then we're going to need our Q values. That's just summing up the Y values. That's going to be 0, 1, 1, 2. Looks like that's going to be 4. Then we're going to sum up the X times Y values. That's going to be our R. So this is telling us we're going to take 1 times 0 plus 2 times 1 plus 3 times 1 plus 4 times 2. And that's going to be, when we sum all these up, that's going to end up being 13. That's going to be our value of R is going to be 13. Then finally, we need S, which is the XK squares. So S that's going to be 1 squared plus 2 squared plus 3 squared plus 4 squared. What's that? 25, 29. Looks like that's 30. And then just put everything into your into the system up here. Just we have up here. So it's going to be 30 for our S. Our P was 10. And then M plus 1, remember, that's our total number of data points, which is 4. And then do AB. And then on the right-hand side, we have R, which is 13. And Q, which is 4. Like this. So we just have to solve this to find A and B. There's several ways you could do this. You could use, like, say, some reduction method. You could change this into equations. There are lots of different ways to solve this. Probably the way I'm going to do it here, I'm going to find the inverse. So again, let's say if we call this matrix A, then A inverse, remember, is going to be 1 over the determinant. The determinant would be 30 times 4 minus 10 times 10. And we switch places these two, change the sign of these two. And what is this in the denominator? That's going to be 120 minus 100. That's going to be 1 over 20. I'm going to leave that out because sometimes it's easier to deal with it if we just don't multiply it through our matrix. So you remember to solve this, then we just take AB is going to be equal to A inverse times this. Right now we have AB. That's kind of what we're doing. So AB is going to be 1 over 20. Like this. And if we multiply these out, what is that? Could be 4 times 13 is going to be 52. And that'll be minus 40. And this is going to be what? Minus 130 plus 120. And this will be 12 minus 10. Then maybe finally at the end here is where we want to multiply these out. So that'll be 12 over 20. Let's see, that's same as 6 over 10, or 3/5. And then this is minus, so it's going to be minus a half. So we're going to have A equal 3/5, B equal minus a half. And then keep in mind what our original equation was. It was, and let me be sure to have the right form because it won't be good if we put it into a different form. Our original equation was of the form y equals ax plus b. So our best fit equation to those points is going to be that. We solve for this 3/5. We solve for A and B, and that's going to be, this is the best fit line. Next, we'll do a best fit to a slightly more complicated equation. So suppose you have an equation of this form here, where we have f of x equal a sine pi x, b cos pi x, and we want to fit this data, do a best fit to this equation here. And so this time, of course, what these would mean, this, of course, is pi x here. And now this time, again, we're going to have, like, say, just two constants we're going to fit. So we'll follow the same procedures before. It's going to look a lot different, but it's going to follow pretty much the same steps that we did for our straight line. So let's take a look at this. So again, if we do our solution, so with this, what we have right here is y equals a sine pi x, just to put into the terms that we had before, and b cos pi x. And I believe I got this example from a textbook. And so we want to do just like before. Let's say if whatever A and B we picked, let's say that our data points were on the line, then, if we were to rearrange this like we did previously, let's say we have A sine pi x plus B cos pi x minus y is 0. And again, if our points x and y are right on this curve for the A and B we picked, then both this side and this side are both going to be 0. So just like before, this is going to be our error. And I'll put that in terms like we had for the previous example. And again, let's say for a particular point, say a particular point xk, yk, and once again, we'll put the absolute values like we had before. So this will be our error. At each data point. Say xk, yk. And once again, we want to minimize this. So we want to minimize the sum of all these. So we're going to follow the same steps we did on the last example. Once again, instead of using the absolute value, we're going to use the square. And so we're going to want that sum, just like we did before, from k equals 0 up to m. We're going to sum all these errors up, but instead of using the absolute value, we're going to use the square of that function. And again, this will be, let's say, our xk, Okay, squared like this. Again, we'll call this, we'll give this function a name. You can give it a different name. We'll call this psi. And just like before, we want to minimize and let me say it this way, we want to pick A and B. To minimize this function. And so then just like before, take derivatives and set them equal to 0. And so again, let's go through here to the psi with respect to A. Again, we have the chain rule like we did before. And then the derivative of the inside with respect to A, that's going to give us sine pi xk, like this. And then do the same thing over here. Derivative, bring the 2 in front. Then the derivative with respect to B of the inside. And that's just going to be cos pi xk. And we want to set both these equal to 0 because remember, we want to minimize this. So we set these equal to 0. And once again, this 2 is multiplied by everything here. So we can divide both sides by 2. Same thing over here. So we can cancel that out. And much like we did before, we want to rearrange everything. We're going to put this sum inside. And so let me just make a line here. And also we want to multiply this through. So let me, once again, we want to solve this for 0. So we can ignore this left-hand side. And again, I'm going to multiply this in. And then, multiply the sine times this, times this, times this. Over here, the cosine times this, this, and this. Then also distribute the sum. Okay, so again, I multiplied the sine through here, got sine squared, cosine, and then I got y sine pi x. Now, this was negative. I moved this over the right-hand side, made it positive. And also, again, I distributed the summations to here, and then to here. Then, like I said, I moved this one to the right. And then also, I pulled out the A, the B. There's nothing to pull out here. Same thing down here. I multiplied this through sine, cosine squared, y cos, and I moved this one over the right-hand side like this. And I was sort of lazy. I didn't put my indexes on, but we know they're going to be from 0 to m. So this is what we have. And so let's go ahead and now put this into a matrix like we did before. So again, I pulled out the A and the B and put this into a matrix. Again, I pulled A, B here, and we're left with sine squared cos times sine. Then down here, cos times sine or sine times cos, same thing, just reversed. These are just reversed. Over here, cos squared. Right-hand side, we have sine and cos. And we can give these names if you want, or just keep them like this. It's up to you. I'll do the same as before. I think we called, these are both the same. We called those P. We called this S. We called this, what did I call that previously? Well, that's right. Last time, this was just M plus 1, but notice that didn't come out to M plus 1 this time. That just ended up coming out to this value here. So we didn't have, this time we didn't have quite symbols form. So I have to give, we can give this a name too if you want. So again, if we call this one up here S, and again, this is P, and we'll call this maybe H. And then we have A, B, and the right hand side, I think we call those R and Q, like this. And again, now we'll just do our data, apply our data. So we're told up here to sum up S, which is this one, or like I said, or you could just, you don't even have to put these letters. You can maybe just call it sine squared pi xk, like that, if that's easier. But in any case, what it's telling us is to put our data points in and then add them up. So what are our data points? -1, -0.5, 0, 0.5, and 1. So just put those into sine squared. Like this, and just double check. I put -1, -0.5, 0, 0.5, and 1. When you put all these in the calculator, again, this is going to be 0, 1 squared, 0, 1 squared, and 0. That ends up being 2. And then for P, we have the summation of cos pi xk sine pi xk. So just put our data points in. We have cos negative sine negative pi plus sine -1/2 pi cos -1/2 pi, and then plus cos pi sine 0 plus cos 1/2 pi sine 1/2 pi plus cos pi sine pi, like this. And that's going to be 0. Excuse me, over here. This is going to be, the sine is going to be 0 here. over here, the cosine is going to be 0. This is going to be 0. Here, the cos is going to be 0. Here, the sine is going to be 0. So those are all going to be zeros. So this one ends up adding up to a big 0. And what else did we have? We also had what we called h was the sum of the cos squared. Once again, put our data points in -1, -0.5, 0, 1/2, and pi. And of course, let's see, this one up here is going to be -1 squared, which is 1, 0 squared, and this will be 1 squared. This will be 0 squared, and that'll be 1 squared. So that's going to all be equal to 3. And then we still have a couple more to do. We have r over here. Now notice this time r involves both y and x. So we're going to have to use our y values too. Remember this pair, then this pair, this pair, this pair. So you stick all those in. And that's going to be -1 sine minus pi plus this time 0 times sine minus 1/2 pi, because y was 0 this time, plus 1 sine 0 pi minus, let's see, excuse me, the next one was a 2 sine 1/2 pi, and finally 1 sine pi. And of course, this is going to be what, 0, 0. This one will be 0. Now this will be 1 times 2. And then this is 1 times 0. So this is all 2. Let me put our answers in boxes here. Then finally, we have one more to do. And that was what we called Q. Once again, that involves both X's and Y's. We have like -1 cos minus pi plus 0 cos minus 1/2 pi plus 1 cos 0 plus 2 cos 1/2 pi plus 1 cos pi. And this is going to be -1 times -1. So it's going to be 1. That's 0. Cos of 0 is 1 times 1. That's going to be 1. And this is going to be 2 times 0, which is 0. This will be -1 times -1, which is -1. So it's going to be 1 plus 1 minus 1. Looks like that's all going to be equal to 1. So let's plug in our values. Again, this was the system that we had, and we just found that S was 2, P was 0. So P was 0. Then we had H was 3. And then R was 2, and Q was 1. And now the inverse of something like this, you can go ahead and double check. There's several ways to solve this. Well, probably the easiest way would be just to multiply this through, because there's zeros here. So this is just going to be 2a and then 3b. Multiply it. 2a is equal to 2. 3b is equal to 1. So it looks like our answers are a equal 1, and b is going to be equal to 1/3. And then let's go back to the form that we were working with. We're trying to put something into this form. So we're trying to put our equation into this form right here. A sine pi x, b cos pi x, and we found our a and b. Now we put them in here. A is 1, b is 1/3, and there we have it. Now in the problems that we did here, we only had like a and b were the constants. You can really do this for any number of constants, just that your matrix will get bigger. So the matrix you have here, if you have like an a, b, and a c, then you'll have a 3x3, and it'll just be a little bit harder to solve the system. But you can maybe find a inverse matrix using some other method and solve for the answer. So that's how you would fit equations to any data. If you're given an equation, like in this case here, we're given this equation. To fit it to the data we were given, you have to go through and set up what you want to find the minimum of. We wanted to minimize the error, and we ended up getting to the point of having this here. Then we, as we always do when we want to minimize something, take the derivative, set them equal to 0, and then solve, and that's how we got to this point.